earlier in the course, we have talked about this rule of thumb for the number of standard deviations that all data lies from its mean, 2 or 3 standard deviations. And at that time, I said that this is a ad hoc interpretation of Chebyshev's rule. Now, here's the moment that all of you have been waiting for. Let's talk about exactly what Chebyshev's rule is. Suppose we have a random variable y, and we're interested in what's the probability that this random variable can be between mu minus k times sigma and mu plus k times sigma. In other words, we start at the mean, we go k standard deviations lower of it, and we go k standard deviations above it, where k is some constant like 2 or like 3, as we had with the rule of thumb. Well, that probability can be shown to be greater than or equal to 1 minus the quantity 1 over k squared. And the key is that this is true for any probability distribution function. So as you can see here, I've gotten a little bit excited about it with 3 exclamation marks. So it doesn't matter what your population looks like. You will always have this being true. So what does this mean? So let's say if I have 2 standard deviations, if I take 1 minus 1 over k squared, I get 0.75. So in other words, we would expect 75% of all possible y values in our population to be within 2 standard deviations of the mean of all those values. For 3 standard deviations, for k equals 3, we would expect 89% of all observations. Now, you might be thinking that this is kind of low, corresponding to how I've stated the rule of thumb in the past, and when we've actually kind of seen its application. But the key is here, this is greater than or equal to. So in fact, that probability could be actually much larger. And in many, many, many cases, it is. Okay. Now, if you wanted to do a formal proof of this, you can find it in a number of different textbooks. So for example, there's a proof available in Kessellenberger. I'm not going to go through the proof here. I don't think it's worth our time to do that. And also, it requires the introduction of some other material too. Now, just to tell you that just recently, when I've been writing a paper, I've actually ended up using Chebyshev's rule to do something. If you're interested in seeing how I did it, take a look at my text that is copied from one of my papers. So let's look at an application of Chebyshev's rule once again, but now with respect to the transaction, with respect to the transaction time. And here's what the PDF looked like again. And let's actually find the probability that, in this case was a random variable x, is, let's say, k standard deviations lower than mu and k standard deviations above mu, or the mean. And one can go through the formal integration to do that. Now we do know that mu is 30, sigma is 30. I'm just writing that in a more general sense. And one can go through the integration, and this is what actually we end up getting. Now, unfortunately, for some values of k, we know that this lower bound for mu minus k times sigma can be less than 0. So in that particular case, let's just take it to be 0 as that lower bound, because we know that x can't actually be less than 0. So let's now actually look at what happens with respect to this transaction time example, where we look at Chebyshev's probability for a particular value of k and what that actual probability is. And I'll let you look at the details on your own of how I've used integrate to do this. In R, we've used it many times before already, so that's why I'm not going to go through the details. So again, Chebyshev's theorem says within 2 standard deviations of the mean, you would expect 75% of all possible values in the population. In other words, the percentage of the values in the population should be at least 75%. But from our actual PDF itself, one can do the integration and find it's actually 95%. Again, Chebyshev's theorem gives you that lower bound. When we go up to 3 standard deviations, we get 98%. And you can keep on going up to 4 standard deviations, 5 standard deviations. So in what we see here is with this PDF, we can actually get something that's much higher than what that lower bound for Chebyshev's theorem gives us. So anyway, so this is a really brief introduction to what Chebyshev's theorem gives us and helps to justify how we've been using this rule of thumb for the number of standard deviation. All data lies from its mean.